This is work I did in collaboration with Henry Corrigan Gibbs and Brian Ford from Yale University, both of whom are in attendance today, as well as Aaron Johnson from NRL, who was unable to make it. In practice, anonymity depends on large numbers of users working in concert together. And if we work with strong anonymity systems, but they have a small amount of users, this can actually produce weaker anonymity than, say, weak anonymous systems with many users. Let me give you an example of how this really works out. We can consider a user, say Bob, who wants to host a party in the park. And unfortunately, in Bob's region of the world, this is prohibited. And so when the authorities find out about Bob's goal to host a party in the park, they arrest him and throw him into jail. Bob says, well, what if I go and I start using strong anonymous systems? And so he goes and finds a few of his close friends, and amongst them, they distribute this message that says, let's have a party in the park. Now, the authorities don't know who is responsible for this message, but they do know it came from one of these sets of individuals. And because there's not a lot of them, the authorities can easily just throw them all into jail. So Bob here is getting really frustrated. He's tried 2 attempts to get this party going, and he really wants to make it happen. So what does he do? He goes one step further, and he uses a weakly anonymous system using everybody in his region. And now when he goes and says, let's go host that party in the park, well, the authorities don't really have much of an option in throwing everybody into jail. There's just too many people. So as a result, they just go to the party and they try to break it up and send everybody home. In general, anonymity enables communication of sensitive ideas without fear of reprisal from governments, organizations, and peers. As a basic tenet of democracy through freedom of speech. So you might be saying, so what about strong anonymity? Why does it need scale, and what's the whole relationship? And in practice, what we've seen is that there's been a trade-off between strong anonymity and scale. And users have favored systems that provide scale, and those tend to only provide weak anonymity. And I'll give you examples of why that's not safe. But in terms of actually making strong anonymous systems at scale, we've set up a series of goals, and we achieve them. And the first being, we want to get strong anonymity that's traffic and timing analysis resistant. We want scalability in terms of hundreds of thousands of active and concurrent participants. We want to make sure that when we're dealing with systems of this scale, that we can handle potential chances for them to just randomly drop off online mid-protocol. And we also want to ensure that if there are people that don't want this protocol to succeed, that they can be determined and kicked out of the group in terms of accountability. And we've done all this in our research work called Dissent. So I've given you the motivation and the goals for our system. Let me go ahead and tell you exactly where existing approaches have left off. The first approach I want to go over is called Tor. You might be familiar with Tor. This is by far the best well-known anonymous communication project out there. And in Tor, there are a series of servers. The server's goals are to assist a user, such as Bob, who wants to relay anonymously his message about his party in the park. So if you look at this system, you can see the purpose of these servers is to make it unclear who is the originator of the message and where that message is going. So if we look specifically at server 01, the middle server, you can see in a Tor-style system, server 001 only knows the immediate hop before it and the immediate hop after it. It has no idea that Bob sent the message, nor does he know it's going to the public server. And in practice, Tor has actually scaled up to well over hundreds of thousands of concurrent users using thousands of servers. However, Tor is not timing analysis resistant. If we assume that Bob is inside of this repressive regime and he and his public server where he's distributing his message are connected directly into this the state-run ISP, then we could imagine that the administrator on this network can be monitoring traffic leaving Bob and traffic entering inside the public server. By doing timing analysis and seeing that the message sizes and the message timings match what's leaving Bob and going into the public server, he can easily de-anonymize Bob. And that's not what we want. We want to make sure that we can create systems that protect users. And a more theoretical approach to this is done in terms of DC nets. In DC nets, we have a set of peers, with each pair sharing a pair of secrets. They use these secret coins to produce shared ciphertext, which can be used to construct cover traffic for anonymous message transmission. They XOR all their shared secrets or their shared ciphertext together to construct this ciphertext. And one of these members can transmit an anonymous clear text message by XORing that into their cover traffic. When they distribute all their cover traffic, in Alice's case, her cover traffic plus clear text message, it produces an anonymous clear text message, and all members are unable to identify that Alice was the original transmitter of this message. And so the key point here is that DC nets do provide timing analysis resistance because all members are transmitting the exact same amount of bits, and they're doing it synchronously. So in terms of where we are left off with existing approaches in our goals, we can look at the goals and we can see that no existing approaches have actually come up with strong anonymity systems that scale and can handle the considerations that we need to. And one of the systems up there under DC nets called Herbivore did get scalability, but they did it in an unusual way. The scalability is in terms of overall numbers of users that are connected to the system. However, then they broke up these users into independent DC net groups, scaling up to about 40 or 50 concurrent users. And in terms of anonymity, that's only providing you a small anonymity set because these disjoint groups do not contribute to each other's anonymity. So now let me give you how we've gotten and created strong and anonymous systems, strong and scalable anonymous systems. So we start with the DC nets. And the key insight we use is if we use the idea behind Tor and mixnet type systems where we have servers, we can come up with a new paradigm involving a client-server system where the servers still respect the peer-to-peer nature of the DC net approach in order to obtain scalability. And we do that in a series of ways. We get better computational efficiency. We get significantly better communication efficiency. We have a system that can handle churn, identify disruptors, all the while we still maintain the strong anonymity found in DC nets. So I'll begin with improving computational efficiency. If you recall, inside of DC nets, each member shares a secret with every other member. And that means they have to generate a ciphertext for every member they share this secret with. And that's basically a random number generation operation. And they XOR all these together along with their clear text to produce the ciphertext. In terms of overall system cost, we're talking about approximately n squared computations or about 10,000 random number generation operations for 100 users. And what we saw from our evaluations is that we're paying about 5.5 milliseconds per peer for these operations. If we introduce the server paradigm, we can come up with a much more efficient approach, particularly in favor of clients. In this assumption, we have M servers with N clients. In practice, you might have, say, 8 servers and 2,000 clients. And if in this case, we have each server has a secret shared with every client, and so servers are still maintaining the same overhead as they did in the other DC nets. However, clients only have a fixed number of server shares that they have to maintain, and so their computation overhead has been significantly shrunk down. And if we talk about in terms of overall system overhead, we can see that it gives us order M times N shared secrets and computation costs for the entire system. And in practice, we can see this results in about 1,000 random number generation operations, which is significantly smaller than the 10,000 found in traditional DC nets. But the important thing here to note is that this is what we use to leverage the communication and churn benefits that I'll show you in the later slides. All the meanwhile, as I will also show you, that this does not sacrifice anonymity by moving to this type of a scheme. So with regards to communication efficiency, let's take a quick look at what happens inside of traditional DC nets. Each member has to transmit their ciphertext to every other member. And this is an order n squared communication cost in order to actually produce their clear text traffic. So if we have, say, 100 peers at the same time, we're talking about 10,000 ciphertext exchanges. Clearly, this is the bottleneck in DC nets that has hampered them from widespread use just because of the time that it takes to transmit long ciphertext to every single member in a group. If we introduce the client-server paradigm, we can actually get DC net-aware multicast trees. And let me explain how that works. So if you recall, each client has, or actually I didn't say this, but each client has a single server that they send their ciphertext upstream to. And the servers collect the ciphertext from each client. Then they compute a ciphertext themselves based upon the online set of all clients and XOR these together. So now they've basically shrunk down a whole bunch of messages into a single ciphertext message. They can just then share this ciphertext with all other servers and XOR them together to produce the clear text, at which point they can distribute these back downstream to the clients and the protocol is completed. in terms of what that means in practice, we went from having about 10,000 communications to having 200, or 2 orders of magnitude, or we went from quadratic to linear communication overhead. So we've given you kind of the scalability improvements. Let's go see how these scalability improvements actually make use in practical cases. So if we look at how typical DC nets handle churn, we can go back to the previous example where all peers have distributed messages, except in this case, Alice has yet to do that. So all members are waiting for Alice to send her message so they can produce their clear text. However, Alice disappears. So what can they do? Well, the exact output, if they were to XOR all these messages together, is garbage, because everybody's message has shares within their ciphertext that need Alice's ciphertext to cancel them out to produce the clear text. And if you think about in terms of overall system progress, when users leave, all the ciphertexts that have been both computed and transferred to every user have now been wasted, and we have to repeat the entire protocol from beginning, excluding Alice from these calculations. In the Dissent case, we handle churn quite effectively. So if we imagine that all clients, except for in this case Alex, fail to transmit a ciphertext and Alex disappears prior to transmitting her ciphertext, the servers can easily just time her out. And the reason why this is, and then the servers can make progress without any worry, because the servers have yet to compute their ciphertext until after all the clients that will, within a specific round, transmit their ciphertext. So after the servers have done that, they do their computation, the protocol completes normal, just excluding Alex's disappearance from the protocol. So we've given you all these different aspects. Now what I want to focus on is something that is critical to DC nets, and that's the fact that they're easily disruptible. And by what I mean by that, you can consider the scenario that I showed initially about how DC nets work. And in this case, let's imagine that Bob is actually malicious, or maybe Bob just wants to transmit a message. It doesn't really matter. But Alice believes it's her turn, and Bob is going to go and interrupt it. What does that mean? So they both transmitted a message bit, and now the output is completely undecipherable, and progress isn't made. And it's impossible, just by looking at this, for users to go and figure out what exactly happened. And what we need to do is figure out a way to prove that Bob transmitted the wrong ciphertext without losing anonymity. What we realize is this is really a scheduling problem. What we need is each member to have specific sets of bits that they own within a DC net. And in order to do that, we created a transmission schedule using mixed nets, which are kind of similar to Tor, and I'm not going to get into details, but basically users encrypt an anonymous public key, signing key, they distribute through a shuffle, and that creates a random permutation of anonymous keys. They use this random permutation to specify the order or the set of bits that they own inside the DC net. Now using this, we can go return back to the previous example where it's now Alice's transmission time. And so each member produces their shared ciphertext, but this time Bob is going to try to interrupt again. And so what we did here is we added some integrity checks. And so when Alice's message doesn't pass the integrity check, all members recognize this as a disruption against Alice, or well, against the anonymous entity that is Alice. And what Alice needs to do is somehow share with all members a bit that is safe to de-anonymize that will prove that Bob interrupted her. And so how do we safely de-anonymize a bit? Well, we can go back to that same construction that we showed you earlier with the shuffle, where Alice will now say bit 1 is safe to de-anonymize, and she uses her anonymous signing key to prove that she owns that slot and it's safe to de-anonymize that bit. All members will get out the message and say, okay, let's go ahead and see what the heck happened in that bit slot. So in this scenario, we have Alice will call out her bits, her shared bits, which were 1 and 1 with Bob and Carol. Carol does the same thing, and she has 1 and 1 as well. And Bob's here in an interesting situation. He had 1 and 1, but if you XOR those together, you're supposed to get 0, and he actually transmitted a 1. So he needs to lie, or he can easily equivocate. So let's assume that Bob's going to lie and try to pass the blame on to Carol. And he says, oh, Carol, I was supposed to transmit a 0. What are you talking about? And so Carol needs a method to rebut this claim by Bob. And to do so, she can easily just share her secret with Alice. Alice can recompute the ciphertext produced earlier and verify that indeed Bob did lie. And Bob has been identified as the malicious or disruptor in this group. In practice, this is a bit more complicated, especially since I just showed you the basic DCNet case. The specific details of how we do this inside the client-server model are discussed inside the paper. So we've made great progress. We've gained improvements in computation and communication, the ability to tolerate churn, identify disruptors. And you might be wondering, so what did we trade off in order to get these? So how does that impact our strong anonymity? So let's look back at how DC nets work with anonymity. The basic principle is in the whole key sharing graph. The key sharing graph specifies that because honest users have direct connections with each other, they don't need to know who they are, but because they have these connections, the anonymity set is equal to the set of honest users. In the terms of Dissent, we retain this feature, but with one caveat. If you recall, we have the secret sharing graph where clients maintain secrets only with servers. And so that means that we need at least one honest server in order to maintain anonymity. But again, just like in DC nets, the clients don't need to know who the honest server is so long as there is one honest server. And this is also exactly why the secret sharing graph prevents a malicious upstream server. So when a client transmits its ciphertext upstream, it doesn't need to worry if it's communicating with a malicious server because the secret sharing graph will keep it safe. So now I've given you how we've done all these wonderful things. I want to show you how this actually works out in practice. We wrote it in a Dissent prototype using C++. We used the Qt framework for networking, serialization, and event processing. We used CryptoPP as the crypto library. Now, before I go into our results, I want to quickly show you these results from previous DCNet implementations. And if you look, you can see both these approaches scaled up to 40 members in their evaluation. We don't consider that scalability. What we did is we got 5,000, 2 orders of magnitude improvement over previous evaluations or previous systems. Now, within this evaluation that I want to share with you, and there's many more on the paper, this evaluation was supposed to look at what a instant messaging or Twitter-like scheme might be. So you can envision each member at any given point in time, or with 1% likelihood, is going to transmit a message in each message exchange. And they'll transmit something like 140 bytes. And so if you look at the x-axis, that's the number of clients in the differing DCNet exchanges, and on the y-axis is the time it took for each of these exchanges to take place. We use the dashed line to represent how long it took for the clients to get their messages upstream, and the red line for the servers to process these messages and release the clear text back into the clients. If you look at the 1,000 number of clients, you can see that takes about 1 second per message exchange, and that's pretty reasonable, I think, in terms of getting a strong, scalable anonymity. Now, in terms of actually where we have overhead and bottlenecks, let's first look at the left side of the graph. And you can see this is basically latency limited. We're basically able to transmit the messages. The bandwidth doesn't take an impact. So, but as you go further and further right, you see we get further and further away from about the 200 or 150 millisecond time, and we're upwards to almost 10 seconds for the clients to get their messages to the server. And that's purely bandwidth limitation due to the number of clients that are now participating in the group. Likewise, there's still computation overhead, but the clients don't have it. It's all in the server area. And that's the difference between when the clients finish transmitting and when the servers take over. Now, in actual evaluation, we took a step further and we want to see why are servers paying so much time. And I mentioned this earlier that in practice we saw about 5.5 milliseconds per additional peer in terms of computation overhead. And so if you look at the far right, servers were paying, I think, about 28 seconds for 5,000 clients connected. Let's see. So we also did another evaluation. This actually isn't in the paper. This was done more recently. And what we wanted to do is take real Twitter data set and see how it worked inside of Dissent. So we found a user that had about 1 million followers on Twitter. And then we followed him along with 5,000 of his friends, and this was purely a limitation of the Twitter public API. And we took all the tweets that they published over a period of an hour. And if you check out the red line, you can see that's the time it took for the peers, or that's the number of tweets per minute that the peers did in the Twitter data set. And then we replayed this through Dissent. And if you look at the dashed green line, it's basically on top of the red line. So I had a lot of fun trying to make these two graphs be present without confusing the presentation. But in short words, Dissent was able to keep up with the Twitter baseline, even up to 1,000 concurrent or 1,000 clients online. However, if we look at the verifiable, strong, secure shuffles, especially the one that we used in the case of the key shuffle and the disruption shuffle, you can see that it's extremely slow. And even at just a small amount of clients, I think that's I guess it's 40 clients, it doesn't even keep up with the baseline system. And as we scale to larger and larger numbers, especially the right end, you can see that it fails to even produce meaningful results within the 1 hour time span allocated to it. And so moving on, we also have some analysis on what it means for churn, and this is where we went to DeterLab. If you're familiar with DeterLab, you remember that it's a pretty awful system to use. It's overloaded. Things are constantly missing or delayed or just disappear, and that's why it's ideal for us to do our churn analysis inside of. And so if you look at the rightmost line, the blue line, that's where we just said, we'll let the system go on as long as possible and just cut off at 120 seconds, and we'll stop listening to clients at that point in time. If you look carefully, you can see that's about 15% of clients never made it to the deadline. And we need to get better than that, so we came up with a few heuristics. Mind you, they're not perfect. They're just to the point to get to nice results. And so if we say, let's cut off at, say, some 99%, or so, sorry, at 1 second, we were able to get 99% of all clients to transmit in that period of time. If we want to be more aggressive, we can cut that down to 400 milliseconds and still get 50% of all clients to participate. Now, in terms of how does the whole system go together, you might recall that there's the key shuffle. The key shuffle isn't cheap. It's not free. And you pay about 100 seconds if you want to do a key shuffle with 1,000 participants. But mind you, you only want to do this very rarely. You're not going to be repetitively doing this. You're going to be doing it once, and then you might do millions or thousands of DC net exchanges before you return back to doing another key shuffle. And if you look very carefully, you might see above that the DC net line. And if you look, that's just a sliver of time in comparison. And if you recall, we're basically paying less than a second, even at the rightmost side of that, for the DC net exchange. Then I also mentioned that there's the blame or the accountability exchange, where Alice wants to point out that somebody corrupted this bit. And this is actually quite expensive because we have to use a different shuffle than the key shuffle, because we have to, this is more of a mathematical thing. I'm not going to get into details, but what we saw is that 1,000 clients, we were paying about an hour for this shuffle. So clearly this is a place where we could definitely use improvement, but nevertheless it works, and that's the most important thing. And after they finally do this slow blame shuffle, there's a small little part where they go and announce whose bits are what and whatnot, and that is a sliver of time again. So if we can shrink that down, we can get an efficient, accountable system. So I've given you the evaluations, and I want to say here are the key takeaways from what we did in Dissent. The most important thing is we can construct strong and scalable anonymous communication systems. And we did this by first looking at communication, reducing that, reducing computation costs as well. We figured a way to handle churn inside of within strong anonymity systems. And we did this all while still being able to provide an effective means to identify disruptors and continuously make progress inside the protocol. In comparison to previous approaches, we were able to gain over 2 orders of magnitude in terms of scalability over previous approaches. All the while, we maintained the strong anonymity properties that existed inside of DC nets. But there's still lots of work left to be done. Most importantly, I want to point out that this would be ideal to get out into the real world and have users actually making use of it through applications and getting them involved. At this point, I'd like to take questions and also point out that you can find out more information at our website, and we'll also be at the poster session tonight, and I'd be happy to have conversations anytime throughout the day. Thanks.
Mike Wildfish, UT Austin. So you have a certification authority in your system, right? Like the paper says that there's some server that knows the public keys and presumably the identities of everybody even participating.
Right. So in the current approach, what we had was a kind of a leader, and mind you, this isn't necessary, but you could distribute this across all the servers, and you could have members register with each server, and they would keep track of all the public keys inside the system.
Okay, so I have 2 questions. One is related to, well, all right, so the first question is 2,000 people really too many to throw in jail? Because your claim about strength in numbers is that, in some sense, it's very clear when somebody's a member of Dissent, right? And actually, so it's clear when somebody's a member of Dissent, it better be true that the level you scale to, 2,000 clients or whatever, is larger than the number that could be thrown in jail, right? That's what you said.
I mean, this is all arguments, right? Unless if we have evidence that suggests that it's not, we can't go one way or the other, and I agree. Certainly, we want to make sure that we have a large enough group that makes it difficult for extreme punishment to be applied to those sets of individuals, right?
Yeah. Okay. So let me just ask a technical question.
Okay.
Then. Is there a way to compose what you've done with another mechanism that would actually hide whether somebody's even participating? That's what's behind both of these questions.
Okay. Well, so currently in Tor, they're actually making progress towards ways to hide the traffic, to censorship resistance and whatnot, to make it look like a user might just be connecting to a web server, and that traffic would then appear to be just web traffic, and the user would be able to hide that they are part of this anonymous communication system. Of course, we still have to worry about that you're going to be playing an arms race, because every single time that we make an improvement inside of these sort of systems, that the adversary can look at it and figure out exactly maybe an optimal way to discover these type of messages. And so it's a difficult challenge, certainly. But it is possible, at least by playing an arms race.
Okay, thank you.
Mm-hmm.
Saurabh Bagchi from Purdue University. So in your baseline, you showed that Tor could be vulnerable to timing analysis. And in the picture you had, the state-sponsored ISP controls all the servers in between. Did I get that right?
No, I'm sorry. Let me bring that up real fast. So the point here was to state that Bob and the public server that he was posting to were connected to the state-sponsored ISP. And the servers themselves are running potentially in the free world. They could be anywhere. It doesn't really matter in this example. The entire point was the traffic that leaves Bob and the traffic that goes into the public server is capable of being monitored by the state ISP.
Okay, so just the edge server.
Yes, just the edges.
So in your case, you have a sort of trade-off between how many servers you want to deploy and the amount of privacy that you would get from it. Because if it's possible to compromise all of the servers, then the privacy guarantees break down. But your communication cost is proportional to the number of servers that you have.
Okay, so let's see if I can pull out what the questions are. So in terms of security, so one way of looking at it, security is definitely dependent on the amount of servers, but if we assume that there's at least one server and we can distribute the servers, anybody can potentially bring on a server. And so it's reasonable, I think it's a reasonable assumption to state that we should at least have one on a server if we have a sufficient amount of users inside the system. The other aspect is that assuming that we have this one server, the security is also dependent upon the amount of clients that are connected to the system, the amount of honest clients. And then in terms of performance, one of the graphs I didn't share, actually I can probably jump to that real fast, is what we saw in practice was, depending on the type of traffic, the amount of servers didn't actually play a significant role in the system, whereas when you look at the other type of traffic, they do. Let me pull that up if I can find it real fast. But, so in other words, I'm not going to try to find it, but what happened was with these small little tweet-like messages, instant messaging, the servers didn't really play an impact regardless of how many servers were in the group. But when we looked at something more like transmitting large files over a period of time, the amount of servers definitely did, and that's totally because of the bandwidth relationship.
Thank you very much.
Thank you.